In this video, we're going to cover research strategies, specifically what we'll call the quasi-research methods. This will cover everything outside of an experimentation, and then we'll look at some basic statistics that you need to know for the AP exam. Before we get started, let's do a quick review of what we mean by an experiment. An experiment is a type of research method. It is not the only type of research method. Experiments also come with their own flaws, like they can be artificial, or they can be completely unethical to run. Because an experiment gives us a cause and effect statement, often we feel more comfortable with the data that's derived from them. However, we can derive data from other research methods, and they can be equally important and equally effective means to gather information. Anything that's considered non-experimental is going to miss out on the established controls of the control group and the experimental group. In other words, there isn't going to be a manipulated independent variable, which will then be measured by a dependent variable. Another couple of things that we should review from the last class. One, when I say operational definitions, you're going to tell me the reason that operational definitions are necessary are because they allow for replication. And for experimentation, but even for many other research methods like surveys, we do still desire replication. Another thing that we had mentioned is the idea of confounding variables. Well, if you want to eliminate confounding variables, the easiest way to do that is with random assignment. But again, that's indicating that we're talking about a control group and an experimental group. But just randomly assigning people to any group, including surveys or other forms of research, has value. The last thing that we really talked about was the only thing that can give you a cause and effect statement is going to be an experiment. But we also said that we very much believe that smoking can increase the chances of developing lung cancer. So much so that today we don't even really say increases, we say smoking causes lung cancer. It's an incorrect statement. However, that would have come from something that we're going to talk about first, which is a case study. Case studies are going to look at pre-existing conditions. This is usually going to be something that is done because of ethical reasons. So we can't manipulate people's smoking behavior. We couldn't set up an experiment where we would take a random sample of a population, take that random sample and put it into a control and experimental group. If we were to do that, we would unethically be manipulating people's smoking behaviors. We would have people who were maybe light or non-smokers and we'd tell them that they'd have to smoke, and we'd have people who were maybe heavy smokers and tell them that they were going to have to go through withdrawal symptoms. We can't do that ethically. We can't also intentionally cause harm. So we can do something like a case study. We can look at people with pre-existing conditions or people with very, very rare conditions and try to generalize from those instances to the greater population. So investigators analyze a collection of consecutive series of case studies to identify patterns that lead to general conclusions. Well, we didn't sit there and try to give people lung cancer, but we did in fact sit there and look at people who were heavy smokers, how often they smoked, and we generated as much data from these cases as possible. A famous case study and a historical case study that we'll talk about in psychology is Phineas Gage. There's a lot of mythology behind this study, which is why we say it doesn't have a cause and effect statement to it, but we do get some information from looking at this single instance. Phineas Gage was 25 years old. He was working on the railroads up in Connecticut in 1848. While he was working, he was setting something with a tamping iron, which is roughly about a 3 to 4 foot metal rod, and he hit a blasting cap. That sent the rod through his head, going the trajectory that you see, just under his cheek and through the top of his head. Obviously, Phineas was bleeding from the head, but no one believed that the injury that he had sustained was what he said happened. He was sent home from work that day, woke up the next day, does not die from this, with a tremendous headache, calls in the doctor, tells the doctor what happened, and the doctor again doesn't believe him. He proceeded to sneeze, and what they said was a teacup full of his brains fell out. What we talk about with Phineas was that the damage to his brain changed his personality. Now, there was no pre-recorded baseline data of his personality. There's no way to really kind of conclusively say whether or not these were people who were adding information in or seeing some change that they wanted to see, but pretty much everyone said that he was a polite, honest young man prior to the accident, and after the accident he was irritable, aggressive, and was more likely to use profane language or to lie. This change in personality led a lot of researchers to believe that different areas of the brain control things like personality, morality, rationalization, all of these other kind of ideas. So again, we can't say cause and effect, but we can sit there and look at this case and go, traumatic brain injury can have a dramatic impact on how a person functions. Today, that doesn't seem like such a crazy idea, but back in the 1840s, this would have been very interesting and revolutionary. Phineas dies roughly about a decade or so later. I've never really looked too much into whether it was complications with his injury or not, but it's still just a very kind of historic landmark case study that we use in psychology. While case studies will look at specific instances that are going to be either unethical to replicate or going to be very rare in nature, correlational studies are almost entirely statistical in nature. Unlike experiments where we have a variable impacting another, in a correlational study, we look at two instances, or even in this case, two variables, but we see how they change in relation to each other. In other words, it's not that one impacts the other, but we're just looking at the data as it exists and we see whether or not there's a trend that tends to appear. So smoking is the easy one, because we always ask, have you ever met someone who had lung cancer but never smoked? And there's definitely a yes for that. Maybe not that you met them, but those people exist. That there's definitely people who've gotten lung cancer but have never smoked. When we talk about correlations, we're seeing whether or not a trend emerges in a relationship between two factors, but we haven't set up this causal kind of experiment. There has been no independent or dependent variable. Another way of looking at something like this is if we were to take a class kind of poll and go, all right, we're going to list everyone's GPA, and then we're going to list on average how many hours of sleep you get each night. We wouldn't be manipulating sleep behavior and then trying to figure out what your average is. We would literally just be looking at the two sets of data, and we'd see whether or not people who got more sleep seem to have higher or lower GPAs than people who got less sleep. Ideally, what we should see, if the trend holds true, is that as sleep increases, so should GPA. But again, we're not setting up any kind of true experiment. We're not making this causal. So we say that a relationship probably exists between the two variables. You should also be aware of the existence of something called an illusory correlation. See the word kind of illusion. A relationship appears to exist, but there really is no relationship between the two variables. Here we have the films that Nicolas Cage appears in the years of their release, and the number of people who drown by falling into pools. And it looks like every time he releases a movie, people kill themselves. But there really is no relationship, even though some of his movies are absolutely awful. This just happens to have a very high overlap, and it can't really be explained because there is no causation. His films didn't cause people to fall into pools, and falling into pools didn't cause him to release more films. So literally, it's just that this really random relationship exists. There's an illusion to it. When we start looking at correlations, it's important that you can visualize what I'm talking about. We take the information that we have and we put it on what's called a scatter plot. And again, you might have somebody who gets a lot of sleep and has a low GPA, and you might have someone who gets very little sleep and has a high GPA. But if we go with sleep in relationship to maybe GPA, you should find that there should be a trend that seems to appear where as people increase in their sleep, they also seem to increase in their GPAs. And it's going to be scattered about. It's not going to be perfectly linear because, again, we're not talking causation, we're talking relationship. Correlations are also measured on the degree of the relation, and it can go from anywhere of a positive one to a negative one. Now, this is something that I always stress in class. The positive or negative tells you the direction of relationship between the variables, not whether it's good or bad. So negative never means bad in psychology. It usually means direction of travel or the removal of something. Positive doesn't mean good, it usually means direction of travel or the addition of something. So a positive correlation would be something like GPA and sleep. Now, we can say it in two different ways. People who get less sleep get lower GPAs. That would be both of those things decreasing. Well, two negatives equal a positive. That would still be a positive correlation. A negative correlation could be something like hours watching TV and GPA. As the number of hours that you watch TV increases, your GPA decreases. As one goes up, the other goes down. One is positive, one is negative, it equals a negative correlation. It just tells you direction of travel. So, the other thing that's important is the idea of anywhere from 0 to 1 is where your relationships are. Now, if the negative or the positive tells you direction of travel, the closer it gets to 1, whether it's a positive one or a negative one, tells you that it's a very strong relationship. The closer that it gets to 0 tells you that the relationship is rather weak. So as we look at this, as the information travels closer to either the perfect positive correlation of 1 or the perfect negative correlation of -1, you see that the information becomes much more kind of closely graphed. The data points are tighter. It gives you a sensation that the relationship is much more kind of continuous, that these things are really kind of reliant upon each other. As you get closer to 0, you start to see that the data points spread and that the relationship isn't nearly as contingent upon each other. There's the variables don't seem to have the same relationship between the two. So the closer you get to 0, the relationship starts to disappear. If you have a correlation of 0, there is no correlation whatsoever. There's no pattern of relationship between the two variables. So we're going to try an example here. Now we have a therapist who has couples and they are looking at whether or not their tests seem to be good indicators of marital happiness. And the results end up being what you see below, test 1, 2, 3, and 4. Now, what a lot of people do is they see for test 1 that it is a negative correlation and they go to a number line and they go, okay, anything negative is smaller than anything positive. But remember, we're not talking about a timeline, we're talking about kind of almost an absolute relationship. So if we're looking at the strength between 1, 2, 3, and 4, which one would be the strongest and which one would be the weakest? Well, the weakest is going to be whichever one is closest to 0. So test 4 is easily the weakest, and it shows that there's very little relationship between the test results and the actual marital happiness of the people who took the test. Test number 1 is going to be the strongest, even though it's the negative correlation. The negative correlation doesn't say that the relationship is bad or that it's weak. It just means that whatever variables were being tested in comparison to the marital happiness, that as marital happiness increased, one of those variables decreased. As marital happiness decreased, one of those variables increased. It is a relationship that's closest to a 1. So it's closest to -1, meaning that it is closest to a perfect negative correlation. At 0.73, it's closer than any of the other ones to 1. Again, it's really important to note that negative doesn't mean bad and it does not mean of lower value. It just means that the variables are maintaining a relationship, whereas one increases, the other decreases. And for correlations, the closer you can get to a 1, the stronger the relationship that is being expressed. Let's try a little bit with illusory correlations. Now, in each one of these instances, you either see a positive or a negative correlation, where the variables seem to travel either in the same direction or they seem to travel in opposite directions, but very reliably so. And as you look at the titles, you could probably manufacture a causal relationship. More iPhones mean more people die from falling down the stairs, and immediately you go, well, that's because people are probably looking at their screens as they approach staircases and then they fall down and die. But that's not what's going on. When we look at the years that are being considered and the advent of kind of fairly new technology, iPhone sales increased from 07 to 10 because there's been kind of a debugging process in that technology and they're more reliable, they're more cost efficient. So yeah, there's been a skyrocket and they're more necessary. And if you look at the elderly population from 07 to 10, we have a whole bunch of the people who would be considered part of the baby boomer generation getting into their 80s. So yeah, they're probably starting to die, which is a really morbid thought on a wonderful snow day. But that might be a better explanation. But they overlap very well. They just don't cause each other. And so you can look at things like let's cheer on the team and we'll lose weight. So consumption of high fructose corn syrup and going to sports games. So you're like, oh, but you jump up and you sit down and you cheer and blah, blah. Again, we can make all of these causal explanations, but When we're looking at them, it's really important to understand that just because you can try to make a causal relationship, that doesn't mean that a causal relationship exists, especially when we're looking at correlational studies. Another research method, and again quasi-experimental, meaning that it allows us to collect information, but it does not allow us to give cause and effect kind of responses, is a survey. Now, you guys have taken surveys forever, and you know the flaws to a survey. You know that you can lie on them. You know that you can give what we'd consider a response set where you give the exact same answer for every single one. But sometimes a survey is going to be the best way to collect information. So it collects information and data and opinions very easily. There's a way to ask people something like, what's your favorite television program? And they could just tell you. They could answer it on a survey. Or you could try to subpoena their, I don't know, internet records and all sorts of other stuff and make it very costly and ineffective. And they may have just been, streaming something that they didn't care to watch, or it just, I mean, a whole host of other issues could pop up. Why not just ask them? Yes, they could lie, but in most cases, when we do take surveys, we try to take them with an eye towards honesty. Some of the other things that come with surveys, just like any other experimentation, the researcher has to be very careful about how they set it up. So researchers for surveys have to be very careful to make sure that the questions that they write aren't skewed or biased towards a particular answer, that their wording is clear and understandable. Questions are usually asked in the same way in order to compare results and draw conclusions. And again, the reason they must be asked in the same way is if you have all of these questions that are being asked on a scale of 1 to 5, with 5 being the highest and 1 being the lowest, and then all of a sudden you switch and you go, all right, now I want 1 being the highest and 5 being the lowest, there may be errors. If you have everything seeming perfectly negative, you don't like this, you hate this, this is the least favorite, and then all of a sudden you turn around and this one positive question pops up, what you might find is that all of a sudden people are drawn to that question and think that maybe that's the crux of your survey. But we all get hung up on the self-report data, but just think about it. During presidential elections and campaigns, we poll, we survey, we ask, and people hold on to that quite heavily. So we do use it, but yes, it can be a major drawback. In class, I would normally do this, and you know how you would probably respond. But there's something called the social desirability effect, that there's a right answer to give to certain questions. And so if I sat there and said, all right, we're going to take a survey of opinions, 1 to 5, 1 being strongly disagree, you don't agree with it at all, 5 being that you really agree, and you have to show all your fingers to the class. I'd feel happy today. Well, most of us are going to put up maybe a 3, a 4, or a 5. We all know that 1 or 2 opens up the person to having people question how they feel, that the teacher may all of a sudden start to be concerned about, your state of mind. You might get sent to the, counseling office. You might get pulled aside for an awkward conversation. So we know 3, 4, and 5, socially correct answer to give. I like people of different races and ethnicities. We know in this one that 5 is pretty much the only answer you're supposed to give. Now, every once in a while someone tries to be funny, and as long as they're well known in the class or people know that they're joking, they may do something kind of outrageous, but we look around and we see how other people would judge that, and so we are very acutely aware that there is one and only one correct answer for that. I feel that men and women should be treated equally in society, and again, this is usually a 4 or a 5. Like, you just know that there's that politically correct, the socially correct response. We do this in other funny ways, like when you go to the doctor and they start asking how often you work out, and you start adding in the fact that you stood at work one day as your workout. Or you go to the dentist and the dentist inquires about how often you floss. We know that there is a correct response to that. It should be every day, but we don't want to be liars, so we say things like, well, I mean, I miss every once in a while, but pretty much like 5 times a week. And so we know that for a lot of these kind of survey, there's certain questions that come with a correct, desirable response. This is what we just looked at in the previous slide, social desirability bias. Literally, there's a desirable answer based off of society about how we're supposed to respond to things. So, tendency to give a socially approved answer to a question about yourself, even if you don't believe it. So we usually think that we're happier, healthier, less prejudiced than other types of evidence would suggest. We like to see ourselves as better people. And a little bit of self-deception isn't bad. It helps with self-esteem, which is a real thing, how you feel about and how you view yourself. So, do you lie to yourself every once in a while? Yes. Do you lie to others about yourself every once in a while? Yes. In fact, you guys are going to get a reading later on that shows that students who lie about their GPAs actually tend to do better in school. I'm not encouraging you to go around and start lying about them, but it makes you feel that maybe you can attain that maybe you can do better, and people seem to treat you differently. And so it increases things like self-esteem, self-efficacy, a couple of other things. And we covered the how often do you floss with the dentist. Other problems with self-report. You could misunderstand the questions. A real survey does not allow you to ask what is being asked, you just take it. Poorly worded questions, those are also going to be problematic. And one of my favorites is the clip, if you want to click on it, from Parks and Rec with Perd Hapley. And it was from what you see on the screen. Do you think Leslie Knope should be in England? Do you not think that? Or do you not think that? And for me, I just laugh at this one because the last 35% were confused by the question. So questions have to be clearly worded. They have to be understood. People may misinterpret them, or they may just be written poorly. And that one is an example of one that's written poorly. The last thing that people tend to get really frustrated with surveys is response sets. And your senior year, you will take a very last senior survey. And you can literally go through and put a response set in. It helps if you give genuine, real information, but I believe that most of us go away knowing that some of it is going to be from people who just aren't interested in taking the survey. So if you're forced to take a survey, sometimes people will in fact just give a particular answer unrelated to the questions. They pick strongly agree to everything, strongly disagree to everything, AAA for everything, or they maybe try to turn it into a zigzag or something. And that does happen. But in most cases, when people are taking surveys and they're genuinely interested in helping, they try to answer truthfully. Another research method that we look at is naturalistic observation. Think of all of those nature videos you've ever watched. No one intercedes, they just watch the animals as they are in their natural environment to gauge how they behave. We can do this with people, but it is limited to certain topics, and it is going to come with its own constraints. When we watch some of these things, we can't intervene, and we could use something like bullying on playgrounds as a good example of naturalistic observation being effective. Kids in an experiment, you could have one kid act as a bully and see if kids react, and that can be really artificial. You could sit there and ask kids their opinions and survey them about bullying, and that again could end up with lies and social desirability effect. I'm a good kid, I would never do those things. You could look at case studies of kids who had been bullied, but again, it may not be something that reaches out and covers all the information that you need to know, maybe about the people who do bully, or maybe it's not that far reaching. So maybe just watching kids in their natural environment, seeing how adults address them, seeing what their behaviors actually are and what bullying truly is at that age, that might be the best way to go. Here's the problem. Once someone knows that they are being watched, they often change their behavior. So, with a lot of the surveillance equipment that we have today, a lot of the different things that we can utilize, we can get really good at naturalistic observation. But again, you would still have to define very clearly what it is that you intend to look at. You need to operationalize your definitions. When you say bully, what do you mean? Do you mean verbal bullying? Do you mean physical bullying? Does your definition encompass both? You also have to find a way to collect data that is still going to have procedures for it. So it can't just be you seeing what you want to see, which is one of the biggest flaws of naturalistic observation. Without constraints employed, researchers might see what they want to see, or they may negate things that could run counter to what they're trying to prove. To remove demand characteristics, subjects should not know that they're being observed. So in other words, they should not have any idea that you're watching them. When subjects are aware, they can alter their behavior. In sociology, we call this the Hawthorne effect, but here, just know that it's a flaw. And again, sometimes it's hard to analyze certain behaviors. So At this point in class, I would normally ask you guys, well, how would you record love? How would you observe the concept of love? And as you sit there and you think about it, how do you know that two people are in love? And so from you guys, I usually get things like they're holding hands or they're kissing in public or maybe they text each other a lot. And it's kind of hard to observe who someone texts. So we sit there and we go, okay, but can you do this? And we can look at things like, well, I've been with my husband for almost, 15 years now. We don't necessarily get all gooey in public, but we usually stand fairly close to each other. We usually maintain eye contact longer when we speak. We have positive, adjectives that we use about each other. We might have to figure out some other way to record love. So it's there. You might have to be very precise about what it is that you intend to measure, because love to one person may not be love to another. And to replicate the naturalistic observation research, you would definitely need to be able to define exactly what concept that you are recording. The last couple of research methods that we're going to talk about have to do with research over time. And the first one's called longitudinal. So just think long time research, longitudinal. And in this one, we're going to look at a subject or a group of subjects, but we're going to follow them for an extended period of time. And I don't mean for a couple of months, but we're talking usually about years. So you may follow somebody from their, early childhood into their 20s, or their 20s into their 60s, or for whatever topic it is that you're looking at. One of the most well-known longitudinal studies that's been going on is the Minnesota Twins research. And it's from the University of Minnesota, and every time identical twins and even fraternal twins are born, they're given the option to register for this. And it's because twins give us some pretty fascinating information about things like genetics. Well, that longitudinal study is going to track twins from birth to death. However, they have some problems with this. One, often subjects drop out. They don't keep following up with the surveys or the interviews in the way that they collect the data. So people drop out of stuff like this. Two, it takes a lifetime to get data for a lifetime. And so that is really, really time consuming. You may have different researchers come in and out, you may have different focuses, and all of this requires funding. So while longitudinal studies are great, they have to have a really extremely important purpose, and again, their biggest drawbacks are they take a very large amount of time, people will drop out of them, and they're expensive to maintain. Longitudinal studies, however, give us a huge amount of data about how a lifetime of experiences can impact a person. But because of their drawbacks, we've constructed other ways of looking at research, and one of them is called a cross-sectional study. Now, if you think of an entire society as being a layer cake, and you have the people who are 10 and the people who are 20 and the people who are 30, 40, 50, 60, and they all make up kind of their own level or layer of a society. And we could look at that person as a 10-year-old and wait for them to grow into their 60-year-old life and cover that entire 50-year span. Or cross-sectional study says, instead of watching one person for 50 years, what if we literally just take a cross-section of the population, find someone who's 10, 20, 30, 40, 50, 60, and pretend that those 6 people are what it would look like to go from 10 to 60 right there in that one kind of cross-section in time. And so you would have 6 different people at 6 different points in life, but they would be considered to equal a single lifetime. This works in some cases, but sometimes the data might not be as accurate. And an example of where the data might not be accurate would be something like technology use. If we looked at technology use in a longitudinal study and we use someone like my mom was born in 1951. In 1951, things like black and white televisions were just coming to be popular. There was no such thing as a home computer, and the internet and kind of touchscreen technology was still something that they only thought about when they watched The Jetsons, which was a cartoon about futuristic people. None of it was reality. So she went through the 50s, the 60s. She got a degree in microbiology. She lived through the 80s with boom boxes and telephones and crazy car phones that actually were part of your car, and into the 90s where a home computer became a kind of normal staple of American life. And then at the end of the 90s, the internet became a normal staple of American life, becoming even far more prevalent into the 2000s. The 2000s, we start to see Wi-Fi and the idea that your technology can travel with you, that you don't have to plug in with a hardwire or a telephone cord, to cell phones that are essentially small computer systems literally in your hand, to cars that navigate and do all sorts of stuff and actually have more computer than car to them now. She's lived through all of this in the last 67 years, 68 years. This is her reality. If we looked at that, we would sit there and say, as far as the longitudinal study, she has increased her comprehension and knowledge of technology over time. If we looked at it as far as a cross-sectional study, and we'll put my mom up there as the 6-year-old and how well she takes on technology right this minute, a 50-year-old, a 40-year-old, a 30-year-old, a 20-year-old, and a 10-year-old. What you're going to see is something that looks a little bit more like kind of a really sad rainbow. Not very kind of steep, just a slight increase and then a very steep drop off. So what we would see is the 10-year-old would have some knowledge of technology, but nothing greater than the 20 or the 30-year-old. The 20-year-old would probably have a vast amount of technological knowledge. Now remember, that 20-year-old in this cross-sectional has only lived with modern technology. The 30-year-old would probably be fairly on par with the 20-year-old. The 40-year-old, for the most part, would be on par with the 30-year-old, but maybe starting to decline a little bit. The 50-year-old would show a much greater decline, and the 60-year-old would show a very steep decline. Instead of it showing a continual growth in knowledge of technology over time, it would show a slight growth and then a huge drop off. So in that particular instance, the cross-section would not be helpful. The longitudinal would tell us more. How do we fix this? We might use something called a cohort sequential study. In other words, we're going to marry the longitudinal study with the cross-sectional study, and what they create is this. We will take that same cross-section, but we'll follow them for a shorter period of time. So we'll watch them for maybe like a year or so. A year is much more doable, and the idea of being able to maintain and track and keep subjects in, it's going to be less costly, and it'll tell you whether or not the change is coming from the individual or from literally the generational gap. So we'd be able to see whether or not the cross-sectional is what's causing an error, or if the cross-sectional can be fairly reliable. We also want to look at the flaws for evaluating research. Now, this isn't just talking about experimentation, we're talking about all research. Replication is going to be utilized in pretty much every experimental and research-based method, with the exception of case studies. We'll collect more case studies, but because of the ethics involved in their nature, replicating them is not possible. But you can replicate a survey, you can replicate a longitudinal study, you can replicate a correlational study. The entire idea is that it should, if it can be replicated, should come with very similar, almost identical results. And if it doesn't, if there is a huge amount of deviation between the results, then something went wrong in one of the experiments or one of the research methods. Something happened that made one of the findings erroneous. We also look at sampling bias. Whenever we do research, whether it's a survey, whether it's longitudinal, whether it is, again, a correlational or even an experimentation, we look at a population that we're interested in. We define the population, let's say all high school students in Fauquier County. Then we pull a sample. The sample should be a good representative sample of all high school students in Fauquier County. So that includes homeschooled, private schooled, from the 4 large high schools. So, us, Fauquier, Liberty, Southeastern, all of those would be included. And what we should find is that we should have our demographics roughly mirror that of the U.S. Census for Fauquier County. If we don't, if let's say we want to survey school start times, and the only group that we really look at is maybe a private school that starts already later, they may have no problem with school start time. When we look at something like sampling bias, You're going to have something like a question on your test where it might be Professor Stevens is interested in people's political opinions for an upcoming election. He wants voter age people to weigh in, so he calls them at home between 2 and 3. Why is this, or what is this? And you'd say it's sampling bias because the people who are home between 2 and 3 probably are going to be retirees. There might be college students, but the majority of adult voting age people are at work from 2 to 3 o'clock in the afternoon. So he doesn't get a good representative sample. The sample is biased. It's maybe not pointing to what he wants or proving what he wants, but it's a faulty, erroneous sample. We want to be careful about the placebo effect. So again, sometimes it's with participants' expectations, and other times it's when we use something like a fake or an empty ineffectual treatment. Now, in experimentation, we will use placebos and we'll use them to impact the control group. If we're doing a diet pill study, we'll give the, control group a sugar pill, and the experimental group will actually get the true change, the independent variable, which is the diet pill. But we can look for the placebo effect. If the control group shows the exact same change in weight loss as the experimental group, then it might be that it was some factor other than the medication that caused the change. But if there is no placebo effect, if the sugar pill is literally ineffective and they don't lose any weight, but the people on the diet pill really do, then we can make the assumption that the diet pill in fact works. We talked about the social desirability effect, and again, that is just making sure that when people answer, we don't give them a chance to kind of use that politically correct response, or that we're kind of aware of what it might be. Experimenter bias. When we talk about this, most people think of this as like a mad scientist or some kind of nefarious person who's sitting there intentionally trying to alter their results to get the outcome that they want. Researcher bias is a little more subtle than that, or experimenter bias is a little bit more subtle than that. And those two are really going to be interchangeable, experimenter, researcher. They may, in a naturalistic study, not see something that refutes what they're trying to prove. Not because they're intentionally doing it, it's because they might be more focused on what they want to see. It might be that they change the inflection of their voice when they ask certain questions in a survey, or that they may unintentionally kind of give something away in their body language. So it's not that it's necessarily this kind of overt intent kind of way to manipulate. It might be a little more subtle. It might be something that they didn't intend to do. But either way, they may give away something about their research, or they may skew things in a way unintentionally to prove what they want to see. To neutralize bias, and specifically in this slide, we're looking at getting rid of experimenter and researcher bias, you want to use something called a double-blind procedure. Now, you're going to get an option on your essay, and it's going to say, where was the flaw in researcher or experimenter bias? And how would you fix it? Well, the fix for any researcher or experimenter bias is always a double-blind procedure. Now, some of you guys would be like, great, all I have to write is double-blind procedure. Nope, you actually have to explain what it is. So in the essay portion of your test, you have to not only be able to tell me the correct answer, but you need to provide an explanation. And later I'll talk to you guys about how this is kind of like almost writing an essay in 5th grade. This is what this is what it does. You become very kind of literal. We'll call it scientific writing. A double-blind procedure is the double-blind procedure impacted in this scenario by, and that's kind of how the writing should look. So it's never just going to be that you can label it. You need to label it and explain it. So what is a double-blind procedure, and why does it work? The double-blind procedure should eliminate experimenter bias, and it will actually eliminate participant bias because no one will know what group they're in. So in an experiment, you're going to have your control group and your experimental group. If the researcher involved is unaware of what group they're dealing with, then they really can't influence them unfairly. If the subjects are unaware of what group they're in, then they can't tip off the researcher and they can't act according to what group they think they're in. So let's go back to our diet pill experiment. I could sit there with the class knowing you guys, and I could sit there and run the experiment. I could be the researcher. Now some of you guys would say, no, that's already biased, but this is how it would work. Someone else would come in and give you guys the pill, and the pill would be labeled with a random code. I would have no idea what the code is. You would come in for, let's say, your weigh-in or whatever kind of thing we would be doing to test said weight loss pill. I would write down the number that you have for your pill bottle and your results. Now, since I didn't assign the coding to the pill bottles, I can't decide whether or not what you got was the placebo or what you got was the actual active ingredient. I can just write down the data. Then, once all the data is collected, then I can decode it. Then I would be given knowledge as to which pill bottle was which. And at that point, the data is already collected and the data speaks for itself. Now, you being in the experiment, you wouldn't know whether or not you were in the control group or the experimental group, and therefore you couldn't act accordingly. You would just know that you were taking a pill and you would be coming in for, say, your weigh-ins. So, double-blind procedures work because the researcher does not know which group, whether it's the experimental or the control group that they're dealing with, and the subjects don't know which control group or experimental group that they're in. Both subjects are blind, both groups are blind, and it's not until the very end that they reveal which group that they're in and the data has already been collected. A single blind procedure is usually a more common one that a lot of people are aware of, and it's where literally just the participants are unaware of whether or not they're in the control or the experimental group. That way they don't manipulate the data. But the control for experimenter and researcher bias is always to do a double-blind procedure. That means that the researcher could know their subjects, but since they wouldn't know which group they're in, they would still treat the conditions fairly. Last little bit that we have to get through is statistics. So when we start looking at statistics, this is going to be your raw data. This is going to be, let's say, test scores for a class, and they can range anywhere from 0 to, I don't know, on the next slide, I think it might be 12. So you get the results. They're not put into any kind of format. This is raw data. The next step with data is that you're going to put it into a frequency distribution chart. And here's your frequency distribution chart. It's basically a simple chart that gives you all of the possible scores, so 1 through 12, how often or frequent the answer popped up. So on the last one, if you went through and you counted the number of people who scored a 1, there was 4. The number of people who scored a 5 was 5. The number who scored a 10 was 2. 12 was 0. You'll take your score and the frequency that it occurred, and you'll multiply it. So you have 4 people had a score of 1, that would be a total of 4. 5 people had a score of 3 for a total of 15 points, and ultimately that score X frequency ends up being tallied at the bottom, and a total of 280 points was collected out of 50 participants. Right here, very, very easily, very quickly, you can find your average. The average score of the class would be 280 divided by 50. You can also start to see trends for your central tendency scores. You can see where they were most frequent. So I go right down to the frequency, and I know my score is 6, 7, and 8. Right there, that was the most frequent scoring, with the most common score being an 8. So right there, that's going to be my mode. My median, again, I had 50 of them. I can look at that there was a little low on the 9, 10, 11, a little low on the 1, 2, 3, but somewhere around 6 and 7, I would imagine my mode is my median is going to probably pop up in those. So while it's not absolutely perfect, you can still find data from this, especially when we're talking about measures of central tendency. We will then take that frequency distribution and put it into a histogram. A histogram is just a nice name for a bar graph. However, the AP exam in the past has asked people to represent information in a histogram. They will not use the term bar graph. You get the same representation for measures of central tendency here. Now, it's not going to be as easy to find your mean or your average, but you can definitely find mode and median fairly well. And again, 6, 7, and 8 seem to be the areas where the highest data points are. Measures of central tendency have been discussed on the previous slides, but just to kind of clarify what they are. Your mean is going to be your average, so it's calculated by adding all of the scores and dividing them by the total possible score. So say there's 100 possible points on a test and you score 85 points, take 85 divided by 100 and you have an 85%. Your median is going to be the score that is in the absolute middle of the entire set of scores. And this requires that if someone has a 5 on a test and another person has a 5 on the test, that they're indicated as individual scores. So you would count until you got to the middle of a class of 25, you'd count until you got to the 25th score, numerically kind of distributed, and that would be your median, your middle. And then your mode is going to be the most common, and you saw that on the frequency distribution very easily, the score that happened the most commonly. We will talk a lot about frequency distributions in this class. When we talk about something called a bell curve or an equal frequency distribution, we're looking at the very first one, where the mean, the mode, and the median all seem to kind of line up near the central point. But frequency distributions can be negatively skewed or positively skewed. Now, for me, the easiest way for me to remember positive skew is that it's the only one that makes a P. So if you kind of like look at it sideways, it looks like a P, which means that there are fewer high scores at the end of the distribution, but a large packing of kind of low or unfairly distributed scores near the lower end. The negative distributions literally fall in the opposite, where you have a predominantly large number of high scores with a few low scores that are your outliers. So you should be able to recognize these. Again, read the data below. We look at this and what we're seeing is that the information is not evenly distributed, that there is either a push to the low end or a push to the high end. And again, positively skewed for me, the way I get this one is it's the one that graphs out to look like a P. A couple other measures that you should know are going to be measures of variability. Now the most common one that we know and the easiest one to calculate is range, but this is also going to be the one that is subject to kind of skew from very large extremes. So let's say you guys ask me how well everyone did in the class as far as the test. Now I'm never really going to tell you, but I might tell you the range. I might say the test scores were anywhere from a 25 to a 94 out of 100 possible questions. And that might make you think that there was an equal distribution throughout 25 to 94. However, that 25 might be an outlier, or that 94 might be an outlier. So it doesn't really tell you much other than that there was a range between 25 and 94, and technically the range is a single number. So there was a spread of scores of 65 points, or whatever it might be. I'm not doing the math in my head right now. The other thing that you need to know is standard deviation. Now, you're never going to have to calculate standard deviation, but you should be able to look at a data set and already tell me how large the deviation would be. So to deviate from something means to move away from, to change from, to go away from. We want to see if we found the average score, how much incrementally most of the scores separate from the average. So the way that it would be calculated is a pain in the butt. You would find the average, you would subtract all of the scores from the average, whether they were positive or negative, then you would square those scores, and then you would add them together, and then you would find the root of those, and it just more than what you need to do. But a really simple way of looking at it is the larger the spread of scores, so let's say you have scores from 1 to 25, their average, whatever it might be, let's say the average score was a 12. Okay, so we would figure out how the scores from 1 to 25, how they equally or incrementally moved away from 12. Then let's say you had scores from 1 to 50, and it's the same number of participants, but now their average is going to be a 25. And incrementally, scores from 1 to 50, how much would you have to space them out to incrementally get them to move away from 25? And we would sit there and say, well, obviously there has to be a bigger gap in between the scores 1 to 50 than the original 1 to 25. Really simply stated, the more closely packed your scores are, the smaller the standard deviation. The larger the spread of scores, the larger the standard deviation. Use that rule and it will help you with the questions. Then we have inferential statistics. And literally they're going to make what we call inferences. They're going to take your information and extend it further. So it's used to determine whether two groups are essentially the same or they're different. We're going to make an inference about that. Takes into account the average scores of the group and then their standard deviations. And what we want to see is we want to see that there is, if we're looking for a change, a real or significant change between the two groups. So if I'm looking at my diet pill experiment again, I want my change to be significant. I don't want it to be just slight or minor. So if it is going to be a significant change, we want the chance that it is atypical, that it's due to some kind of chance, it's less than 5%. We want to say that our data is significant. So a concept, or they accept the difference between two groups as real or significant when the probability that it is due to some random chance is less than 5%. So we don't want this kind of atypical random chance. We want it to fall under 5%. We want to see that the change in the data, the change in the two groups is significant and real. The last thing that we'll talk about is going to be ethics. So here's a situation. You have a psychologist who has these people that he may take on as his subjects. His best friend's wife, his graduate research assistant, his wife's therapist spouse, and his daughter's boyfriend's brother. In each one of these cases, the psychologist has a personal relationship or a relationship with someone in that person's life that could somehow alter the therapy or the advice that they would give to the individual. His daughter's boyfriend's brother, well, he may hate his brother's girlfriend, or he may reveal that his brother is suffering from severe whatever, and that may impact the psychologist and his take on how to give this person advice. It might be his wife's therapist spouse. Well, the therapist spouse may be talking to her husband, and the husband might be saying about, how this crazy woman came into work the other day, and all of a sudden you realize that they're talking about your wife. Your graduate research assistant, well, are they getting paid for their research? Are you finding out things that might make you question whether or not they should work for you? And I think a best friend's wife, that becomes self-explanatory. So psychologists can take on people, but if it's someone that you would have a personal connection to, ethically bound to suggest that maybe they go see somebody else, like a colleague. There are ethical guidelines, and in your review book, and if you don't have that with you, it is in the section on Blackboard. There are guidelines that the APA has for ethical code of conduct, and code of conduct literally is some of that you cannot release people's personal information, that subjects personal information is protected. So there was a gentleman by the initials of HM that we talk about when we talk about memory, and HM had been protected for 50 years until he passed away, and then his personal information was allowed to be released. That's how this works. Even in case studies, unless they are giving you explicit kind of release to give out their personal information, you have to keep all things private. Research must be done under the supervision of an institutional review board. This is usually done through either a university or a college, possibly the American Psychological Association. And when we talk about animal use, the big rule for animal use is that you cannot use it just to see what if. It must further science, and it must be done with an eye towards whether or not it is necessary to use the animal. So we'll talk a little bit more about animal ethics here in the next slide or two. With ethics, you have to start every research with informed consent. When you guys get to your second mandatory project, you have to give your subjects an informed consent. They need to know that they have every right to leave the experiment at any time. They have to be informed of any potential risks that they may suffer by engaging in the experiment, even if they are minimal. If they are promised money, they must be paid, even if they choose to leave the experiment. So there can't be anything that is hanging over their head that forces them to stay in the experiment. The other thing, in psychology, you can absolutely lie, but people seem to kind of confuse full disclosure with informed consent. Informed consent comes at the beginning saying, here, I'm letting you know the purpose of my research, and I may even tell you, please understand that deception may be used. You're informed of all of the risks, but I may not tell you the true purpose of my research. Full disclosure, however, is at the end of an experiment or the end of research when I say, hey, thanks for participating, by the way. And so we'll do this especially in social psychology experiments, because if I tell you I want to see whether or not you do what the group does, you're probably going to be a bit more independent. But if I tell you that the purpose of my research is a memory experiment, and then later I come back and say I wanted to see what you would do when the researcher told you to do something, or when the group decided something, I wanted to see if you were going to say no or obey, if you were going to conform or not, that's a bit more telling. So we can lie, we can use deception, as long as at the end of the research we fully disclose to the subject what the purpose of the research was. This should be the last little bit, guys. Animal research. So why we use animals. We might want to learn more about their particular behavior. Now that can be done in a couple different ways, and it's not always with a true experiment, But sometimes we might use a true experiment. We cannot harm animals just to see what they might do, and we can only do things that would further our knowledge that is necessary. So if you wanted to see what would happen if you injected something into an animal and it has no scientific reason, it's not going to help humans, it's not going to help their species, then you can't do it. That's just being cruel. To see whether or not certain laws apply to both humans and animals. Well, again, this is going to be something that we'll look at a lot in behaviorism when we sit there and we look at, do people classically condition? Do we operantly condition? And do these things apply to other animals? Yeah, we can do that, but we still have to do it with a humane kind of focus. The most controversial reason that we'll use animals in research is usually when it comes to subjecting them to things that we aren't quite ready to subject humans to. So chemotherapy or radiation therapy would have been tested on animals prior to humans to see if it even works. Now, when we talk about this, we would sit there and go, some people say, skip the animals, they have no reason to be treated that way, immediately just go straight to humans. And so I don't know if you guys are aware of when PETA came up with the no longer saying treating someone like a guinea pig because it's unfair to guinea pigs. We do sometimes use animals for the simple fact that we may not be ready to use humans. And not everyone feels the same way about that. So that really is an individual kind of thought, and you have to come to that decision on your own. But those come with really heavy ethical constraints, and you cannot just choose to subject an animal to something cruel just because you want to figure out what would happen.